And it will be, I guess, continuing the section that we looked at last time, the ratio and the root tests, just to refresh what we have been looking at. There is a couple of big statements that are in a way similar to each other, conclusions. The root test and the one we looked at was ratio test. So what we do is we compare with 1. So we take the quotient of next term and the previous term and see if it's less than 1, then series is convergent. And it's convergent absolutely. And if ratio is greater than 1, it's divergent absolutely, but may converge conditionally. That's odd type of convergence that we slightly looked at, but did not really try to get into because it's a long story and we never do that here. So we just care for the cases less than 1. When it's equal to 1, it's not conclusive test, so we need to use something else to decide. And analogous results are when you don't divide n plus first by the nth term, but when you are looking at the nth root. And the nth root is definitely useful when you are dealing with examples like 4, where something is raised to the power of n. So that's, I guess, designed for this particular cases. So when you extract the nth root from your nth term of the sequence, those powers of n will disappear, and you're going to end up with no power of n whatsoever. So you're going to end up with e to the second over n, and when you take the limit of it, you'll be able to get some fixed number. And if that fixed number again is less than 1, you have absolute convergence, and if it is not less than 1, then we don't really get anything. So less than 1 is the key idea, and in this case, it's 0, that limit. So let me do some examples at the end of the section to, well, see how we use these tests and how it'd be better and more convenient to use which test is better. Turns out, since we already accumulated so many tests and different ways to determine conversions, then we have same exercise that could be done differently. And sometimes you might use the story from previous sections, sometimes from new sections. Let's say the new idea is when you have everything raised to the power of n, like in exercise 29. So I will be looking at the nth root out of the nth term, and they say take its absolute values, so negatives are not going to be involved at all. So when n approaches to infinity, and when you do that with the term that clearly is everything is raised to the power of n, then definitely it does make a good sense to perform this test, right? Because if I take 6 to the power of n or n plus 1 raised to the power of n, then all of these powers are going to cancel each other, and you're going to end up with a limit of 6 in your numerator and n plus 1 in your denominator. And 6 over n, when n approaches to infinity, will be equal to 0. Right? 6 over big is small, so it is less than 1. So this means that series is convergent absolutely. So absolute convergence is what we really care about, which means it's stronger than just a convergence. And even though everything here is positive anyways, right? 6 is positive and n plus 1 when n starts at 0 is also positive. But we say it's convergent absolutely, so it means it's really convergent. And what's convergent? This convergent, not that one. That one is 0, right? So it's convergent absolutely serious that we have here. What it is convergent to, we don't know. We only know what it is convergent when you're dealing with the geometric series. 1/2, 1/4, so those are ones we can calculate. But for these series, we just say it's convergent, but who knows what it is convergent to? Convergent. So the sum is finite, and that's it. See, it's fuzzy, right? So say, is it possible to calculate the sum? Well, it might take you learning math a long time. For each particular example, you may be able to find, maybe not. So we're not even attempting to do that. But convergence is. Let's say if I look at exercise number 10, then you can say which way to do it. Should I extract the nth root? And definitely you can do it. So you can definitely try to use the same exact formula, the same exact limit for the calculating if it's less than 1, right? So we compare everything to 1. So if you take the limit of the nth limit of the nth term, so I can actually see it's 4 on the top and e to the power of n on the bottom, then you're gonna end up with the nth power of 4, nth root of 4, divided by just number e. And the question will be, is this really more than 1 or greater or less than 1? So this is for conversions. Well, maybe you need to then learn what's nth root of 4 is. Is this more than e or less than e, right? Because it's heavily dependent, because if it is e, then we're going to have 1. But if it is more than 1, more than e, then you're going to end up with something divergent. And if it's less than e, it is going to be conversion. And what's the nth root? Well, turns out it approaches to 1, but there is quite a bit of work. It's a little bit different story. And that's the reason why I selected this example, to illustrate that you could have used the other test. The other test in that section was n plus first term divided by nth term. So it works analogously, but it enables me to cancel things out. So if I take the limit of the 4 over e to the power of n plus 1, right? And divide this by 4 over e to the power of n, definitely I'll be able to simplify these a little bit, right? So when n approaches to infinity is what I care about. See, that's another test. There were 2 tests. N plus first over nth term, if that's less than 1, or nth root. And if you're not sure what the nth root of 4 is, when you say, Alex, I can take the calculator and extract the root. Yeah, you could do it, but to be precise. So it looks like we're gonna end up with the limit, and on the top I can write as 4 e to the power of n times another e, so that's n plus 1. And the bottom part, this is going to be reciprocated, right? So just doing simple algebra. So it heavily depend on doing the algebra. So that's e to the n is then going to be on the top, and e and 4 is going to be on the bottom. And then your limit is definitely going to be clearly extracted, right? And you won't need any extra things about nth root of 4. It'd be way more straightforward. So you're going to end up with a number 4 cancels. So it's just 1 on the top and e on the bottom. So it's like 1/2, something like that, 1/3 in between of these. And this is really 1 over e. Doesn't matter what happens with n, because you take the limit of a constant, and this is less than 1. So this is going to be what? Absolutely convergent, right? Convergent series. So the point of story is we don't have to use some particular test, but using either one is fine. So I would say it's better in general, n plus 1 over n, and the test for the nth root is quite rare. It's only being utilized when both and numerator and denominator raised to the power of n, so you simply drop this power of n, and that's not as popular. But for all exercises like the one we have here with factorials especially, we definitely want to use that n plus first over the nth term quotient. So this makes all exercises to be pretty much the same. You're just applying this test and see if it's less than 1. Right away you say it's absolute convergence. And in this case, in most of the cases, we actually end up with conversions anyways, because lots of times we have positive series anyways, unless we have something like 7 or 8, then attaching word absolute makes sense. Otherwise, it's just conversion. So I'll let you do some more exercises here to verify that this is really all the same story. And this is nice to have those tests, of course. And I will move on and briefly touch section E9.7, because a section after next, which is going to be like 9.9, it will go in more details. So section 9.7, I just wanted to give you, well, it's, let me stop sharing, share it again, clear this stuff. So it gives you the way we're gonna work at the actually section after next. So they split it, the section, into 2 pieces. So I'd rather talk about this next time, which is going to be next week on Tuesday. But since it's here on the way, I think it may be a good idea for you to just consider something interesting. And interesting thing is that you can decompose your polynomials with respect to the power functions. And what this is all about is a bunch of these pictures. So it turns out the polynomial functions, like function f, could be approximated with, so function f, notice the function f is the same in all the pictures, right? So you approximating it with polynomials of degree 1, which is line, or polynomials of degree 2, which is parabola, or polynomial of degree 3, cubic parabola, polynomial of degree 4. And turns out every step you do these approximations, you get better and closer to the actual shape. So the idea is to be able to get it approximated with infinite series. So the first term will be polynomial degree 1, So first degree polynomial, like they have here. And the second step is second degree polynomial squared. And the third step is third degree polynomial. And of course, there'd be a second and the first powers. And so forth, the fourth degree polynomial. So they stop at this section at the step 4, but turns out the best approximation is with infinite series. So it continues x minus 1 to the power of 5, 6, etc., series. So that's where it's heading to. That's why here is finite steps, but in the section after next will be infinite series. And that's I guess, because the part of that approximation here is just stars, and there should be next section, but it's section after next, well, whatever. So they have a reason. So anyways, the idea is how to approximate it with powers, in this case of x minus 1. And the question is, what will be the coefficients, like A1, A2, A3, and how do they produce these coefficients? Well, you say, Alex, looks like they take derivatives. Yes, they take derivatives, and they also use factorials as their denominator. So why is that factorials? And I think it's nicely explained why here, because when you start to differentiate your polynomial, the coefficients, because when you take derivative, let's say you have, for example, x cubed. So if you try to differentiate it, the first derivative will be 3x squared. And if you try to find the second derivative, so you're going to differentiate it again, so the 3 will stay, but that will be 3 times 2 x to the first. You see? 3 and 2, so like 3 factorial. So that's what happens. So if you keep differentiating, but let's say if I did differentiate next time would be already just 6, and one more time it's going to be 0 because there'll be a constant only. Yes, but if you have the powers, the polynomials, you can differentiate infinitely many times, so the powers are huge, a million or whatever, then you can actually get lots of these coefficients, and they will all be with denominators such as factorials, so 4 factorials, 5, etc., n factorial. And that's what they're trying to show, how these appear. So then they decompose it at some particular point, let's say at point 1. So they write it with powers of 1. And notice that when you put 1 in for x, this will disappear. So the approximation is going to be just f of 1. Or if they use the second polynomial, so if they differentiate twice, then f of 1 disappears, and then there'll be f prime of 1 that appears. And that'd be already, so when you plug it in, it'd be leaving us with just, well, I think they wrote it somewhere. I'm trying to say it, but they have it. I just saw it someplace. Oh, here. So they show that if you have the composition, let me clean this mess, with respect to higher level of derivatives, then for each step, you're gonna, well, start differentiating. Let's say if you differentiate the first step, A0, the constant will disappear. And A1, when you differentiate again, x minus 1, the first power of x will disappear, so just A1 will stay after you differentiate it once. But when you plug in whatever the number is, c for x, this will all be zeros. So A1 will be your coefficient in decomposition of first derivative. And analogously, when you take the second derivative, the first derivative term disappears and 2a1s, 2a2s will stay. And when again you plug those c's in, those will become 0, but that'd be twice a2. And that's what they're writing here, and etc. So that's how n factorial will appear with an. And those are coefficients, and that's what we're going to utilize. So that's the key idea in here. So anyways, this is what we're going to utilize a little later. And today I'd like to discuss a little bit the polynomials that are functions. So we're approximating with not just what we had before, just 1/2, 1/4, 1/6, whatever. Those are not functions because those are just sum of fractions. So with a series that fixed at one place. But now we have series that have to do with functions. And that's the different, because when you have a function, then you have variable x that can take any value. It can be 1, it could be 5, it could be 1/2, could be e, could be square root, right? So whenever you have a function of x, this function, in the case of polynomials, is defined for any real number. So this way to write things down is actually containing infinitely many functions. I think a while ago I already tried to discuss that a little bit. So now we return back to the idea that this record is really a record of functions. So the problems that we have in the next section are not dealing with a single series. They are dealing with, I'm going to move to the next section because this is going to be continued. And we're moving into the story of series that have functions decomposing them. So like e to the x could be presented as a infinite series, and it depends on the power of x, depends on the function. So e may be squared or may be raised to the power of 1,000 or -5 or whatever real number you like to use. And the question is, are they always going to converge? All of this series, are they going to be having finite sum or infinite sum? And that's what they call as power series. That's more general type of a problem that deals with not just one series, but with infinitely many series decomposition. So today I'd like to just look at an example to give you an idea. For example, if you look at the series here, example 2. Here, example 2. So they ask us to look at the series n factorial, but multiplied by x to the power of n. So what about x? What x will be giving us the finite sum, and what x will be giving us the infinite sum? So for example, they say in the beginning, what if x is equal to 0? Well, if x is equal to 0, then you're going to end up with a series n factorial multiplied by 0, which is the sum of zeros, because times 0 means 0, right? So sum of zeros, and this is 0. So the series is going to be convergent. But when you say it depends where it starts. So if it starts at the first term that is n equal to 0, then you end up with a sum of n factorial times 0 to the power of n, because 0 put here and 0 put here, and 0 factorial is 1, and 0 to the power of n is 1, so this is going to be first term is 1, so you add in 1 with that 0, because the first term is 1, and your sum is not 0, but 1. Well, whatever. We found the sum, and that's the point. So is sum always going to be finite or not? And the way they check it is they use the previous section story, the ratio test at n plus first term over nth term, where you can say y is not a, why they put u. Well, just to make a distinction that this is not just a numbers, but we have function. So x is variable. So when you start dividing n plus first term by the nth term, looks like as usual you can cancel and you end up only n factorial will cancel, n plus 1 will remain, and that's x to the power of n plus 1 over x to the power of n, so it should be times x, and if you take the absolute value, it should be absolute value of x. So what do you get when you take this limit? Well, n goes to infinity, so no matter what fixed number x you multiply by infinity, the result is infinity. So it's never less than 1, which means that this is divergent. So it's divergent everywhere else. So only when x is 0, so only when your series looks like 1 plus 0 plus 0 plus 0 plus dot dot dot, it is convergent. Otherwise, it's always going to be divergent for any value of x. And you say, really? Yeah, you can try to take x equal to 1, for example. What if x is equal to 1? Just to clarify, see, it's very abstract, but if x is equal to 1, then your series n factorial x to the power of 1, right? Because it's actually 1 to the power of n. Sorry, 1 instead of x to the power of n is going to be the same as if you have a series of sum of n factorial. So you're adding 1, 0 factorial, then 2, 2 factorial, and 3 factorial, and 4 factorial. So you just keep adding this factorials, and of course, they're going to infinity, right? Because n factorial is larger, you keep on adding. So if x is 1, if x is 2, is even bigger, because instead of multiplying by 1, you'll be multiplying by 2, so it'd be even bigger than that. So it looks like it is always going to be divergent. So when you say that's for n equal to 1, what about n is equal to square root of 2 or whatever? Always, no matter what. So it is divergent for every value, except for the case when x is 0, because then the series turn into zeros, right? So we doing a big thing. We're able to calculate now the sum of not just one series, but infinitely many various series, real number of series, which is quite amazing. So I can take a look at sample 3, and maybe I'll stop at this stage. I know it's very overwhelming. How come we are dealing with so many series? Well, that's the way it is. So if you take a look at the series in that format, then what you do is look at the favorite tests and see when it is less than 1. So you divide n plus first term by the nth term, and you put n plus 1 for the n plus first term for the power, and then the previous is just power of n. And notice that we have 3, and that's x minus 2 on the top to the power of n times x minus 2, because the power of numerator is going to be your n plus 1. So you can separate one of these parentheses, right? And denominator is going to be nicely then canceled with this same nth term for numerator. So you're going to end up, and 3 is also going to cancel. So you're going to end up with just x minus 2. And you're taking its absolute value. And this is going to be absolute value of x minus 2. So now the key part. When is this less than 1, then it is going to converge. And that's what they say. The series convergent, according to the nth term test, when the limit is less than 1. So now you need to solve your inequality, right? So how do I solve this inequality? X minus 2 in absolute value, x minus, not plus, minus. And absolute value is less than 1. Well, just the way we used to solve the inequalities, you get rid of the absolute value, right? So we have it in between plus and minus 1, right? Let's say I forgot why. Well, if assumption is an absolute value less than 1, then it must be in between, but not including plus and minus 1. So it has to be here, anywhere. So the number must be in between plus and minus 1. If it's more than 1, its absolute value is more than 1. Or if it's less than negative 1, so it's big negative, so its absolute value is also going to be more than 1. So it has to be in between of these two. And then I will add 2 on both sides, right? That's how we used to solve it when took algebra classes. And the way we do it is we increase by 2 each part of this inequality. So when I add 2, the result is going to be 1 on the left side and 3 on the right side. So for x values on that open interval, we have absolute conversions. And everywhere outside of this interval, it's divergent. And please notice that the radius of this interval, so if I look at interval between 1 and 3, I go by 1 from the center to the left and to the right. That's called my radius of convergence. It happens to be equal to 1. So radius of convergence is the, I guess, from the center, how far we can go to the left and to the right. And say, why do they need this radius of convergence? Well, I guess that's popular kind of question, but that's the actual interval. I guess that makes kind of sense. But radius is definitely 1 to the left and to the right. So I'll do one exercise so we can see how we find those radius of convergence by doing the same procedure for all exercises. So the good thing is that's pretty much same for all. So maybe I can clear this mess, or I can just select an exercise. So how about if I try exercise number 12? You can clearly see exercise 12. So see if it's convergent or divergent, and then next step will be to find this radius of that conversion. And again, how do I do that? Well, I look at the standard process. So I look at nth plus first term over nth term, or u, doesn't really matter, the absolute value. And now we're going to put this x to the power of n plus 1 over 7, right? To the power of n plus 1, and divide this by exact same, but raised to the power of n. It looks like they will nicely get canceled, so you're going to end up with a limit of x over 7 in absolute value. When n approaches to infinity, notice there is no n here whatsoever. So you just have x over 7 in absolute value. Right? And now next step, make it be less than 1, then it's conversion. If it's less than 1, it will be absolutely conversion. Please notice we're using absolute values, so absolute conversions make sense. And now I solve this inequality by isolating x, because we need to get x, and the end solution is always the same. So it looks like I multiply by 7, right? Just do some algebra. Multiply by 7, and I see that radius of convergence is 7, right? Because we're from -7 to +7. So we're in between of minus and +7 here. So from 0 I start, then 7 is going to be my radius of conversions. 7 to the right, 7 to the... Just like that. So it looks like this problem could also been done, and that's interesting observation, by using the nth root. Because the whole thing is raised to the power of n. So you could have extract the nth root, in other words, lose your nth power in here. And once you lose your nth power, you would end up with x over 7. So you would end up with the same exact inequality if you applied a different theorem for conversions. And as usual, no matter what theorem you use, the result is the same. So it is really up to you how you solve it, because the answer is going to be still the same. Radius is still going to be equal to 7. So for convenience, you can decide. So looks like, again, if that's 7th power here or 7th nth power everywhere, then you use that nth root. But since here we have factorials, definitely nth root is not a good idea to use. Then you use the quotient. But again, the quotient is working pretty much for all problems anyways. So let's stop at this stage. I guess this is a good moment to stop my recording for today and see how you feel about this, if you have any feeling at this stage. And we'll continue, we'll do another exercises from 9-8, and then we'll look at this stuff we started prior to it, those so-called Taylor and then general Maclaurin polynomial decomposition. That'd be the last time we see